Okay, trig identities. I'm not gonna lie, this is not easy. We're gonna spend a couple of days on this. We're gonna really hit it hard, and you're gonna get some to try kind of on your own for free, and then you're gonna get some to try on your own for points graded like a quiz. If you actually watch this, you'll be a little ahead of everybody in knowing that, because I'm not gonna say that to everybody else. Anyways, so the first thing I would have you do today is to do the warm-up, which is this A, B, and C thing here. What is the number of possible solutions to a system of two linear equations? So if I think back to elimination, substitution, and I get a linear equation. Well, linear equates to lines. Lines go like this, and somewhere those lines cross, unless they're parallel lines. So that would be, example 1 would be no solution. And that's when you have parallel lines. Okay, no solution. 2 would be one solution, like you can see up above in my picture, is when they are intersecting. They don't have to necessarily be perpendicular, although perpendicular lines do intersect in one place. All lines are going to intersect in one place if they're not parallel, and if they're not, so I'm going to put including perpendicular lines. Now, 3 is infinitely many. I'm in Mr. Vartanian's room, so when you hear the door or some other stuff going on, he's busy working some things out here. So infinitely many means if they're the same line. And we're going to see that occur sometimes today. That's where kind of identities come through. Now these are called parallel, intersecting, and coinciding. Do I expect you to remember that? No, because we haven't done that this year. But next, it says Collins type 1. What do you think of the number of possible solutions for two trig functions? Think of what these graphs look like, those waves. And not even thinking about tangent. Tangent is crazy. But sine and cosine are both waves, curves, right? How many times are they going to cross? Well, number 1 could be no solution. Okay. If you have a graph moved way up and you have a graph moved way down, they're never going to touch each other anywhere. So no solution is one possibility. The second one is infinitely many. In other words, if they're the same graph, I could have sine of x and I could have cosine of x minus pi over 2. And I've talked about how those look the same if I just shift one over 90 degrees or pi over 2 radians, and they become the exact same graph. So that would, even though they look different, they would be the same based on the shift. And the third one is infinitely many periodically. So if I get a graph of sine, up, down, down, and up, and I get a graph of cosine, that looks like a ditch, they keep intersecting here, 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 and it would just keep going in both directions. So that's what I mean by periodically. I'm going to have you take your Chromebooks, not your iPads, and graph the following system separate and see what you think. Now you need to have it in radians if you're using a graphing calculator, but if you use your Chromebook, you can just go to decimals, and I want you to graph each of these. Go ahead and take a second, press pause, graph each of these on the same line, and I just kind of want you to describe what you see just right here in this blank space. Then I want you to do it separately for this problem. You're going to graph that, you're going to graph that, and you're going to tell me what you see. Press pause, try that a second, come back, check it out. Okay, so hopefully you did it, and you're going to realize that they are exactly the same function. And specifically for this one, they're exactly the same line. They're just a horizontal line there going through y equals 1. They are equal, so they are identities. And that's what this section is all about, identities. Okay? So a trigonometric identity is a trig equation that is true for all values except those for which the expression on either side of the equal sign is undefined. So the equations cosecant equals 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent, the stuff that we did yesterday, are known as reciprocal identities because they are equal to each other and one's just a reciprocal of the other. We could also actually say that cosine is 1 over secant, we could say tangent is 1 over cotangent, we could say sine is 1 over cosecant, and so on. Many of the trig identities derive from the unit circle itself. You may remember from this picture from 10.5, from 10.8 notes, etc. And remember that cosine is just my x value and sine is just my y value. So from this picture, well, Pythagorean theorem to solve here would say x squared plus y squared equals a squared plus b squared equals c squared, really, is what I'm doing here. A squared plus b squared equals c squared. Now, we know that 1 squared is just 1. But if I replace x with cosine, then x squared would be cosine squared theta. Y squared would be sine squared theta. And that equals 1. And that's why when you plugged this into your calculator, well, it was just a straight line at 1 just like this one because they are identities. That's one of them, okay? There are 3 total, and we're going to verify them down here. These are notes that you're just going to have to trust me on and stay with me. The next one is this one right here. Let's box that in because that's the next one. And how are we going to prove this? Let's just prove it by just using stuff we know. So this is 1 plus tangent is sine squared over cosine squared. Okay? Secant, well, I'm not going to worry about that because that's what I want to be my final answer. So to be able to add these, well, to be able to add anything with fractions, I need a common denominator. And that common denominator is cosine squared. So if I times the bottom by cosine squared, I got to times the top by cosine squared. And I get cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta, which I have a common denominator, so I can just write that on the bottom. On top, I get cosine squared plus sine squared. Yes, I'm leaving out my theta to just work with something here. Well, cosine squared plus sine squared, we said right here, is 1. So I can replace that with 1 over cosine squared. 1 over cosine is secant, so 1 over cosine squared is secant squared. And that's what I wanted. That's what I get. Okay? Let's do the next one. That's it. That's the answer. My final answer when I'm trying to verify is just whatever it's telling me to equal. So this one I want to get cosecant squared. So again, I'm going to go 1 plus tangent is sine over cosine. So cotangent is just the reciprocal, cosine over sine. By the way, let's put a box around this. That's going to be, now the same kind of rationale here, I'm going to have a common denominator here, sine squared, sine squared. I'm going to rewrite this all together as 1, so sine squared theta plus cosine squared theta all over sine squared theta equals. Well, on top, that's 1. We said that before, cosine squared plus sine squared, over sine squared, which is, well, 1 over sine is cosecant, so 1 over sine squared is cosecant squared. And there I get what I want. This one's a little more difficult, but not really if you start looking at it. Squared means to times it by itself. So I have sine of x plus cosine of x times sine of x plus cosine of x. And I'm going to FOIL this out. Sine times sine is sine squared. Cosine times sine is cosine x sine x. And then I've got another one. And then I've got, so that was this one. And then I've got cosine times cosine to give me cosine squared. Alright, so one thing I have to see is I can combine like terms here. I get 2 cosine x sine x because there's one here and there's one here. Now, what does this give me? Sine squared x plus cosine squared x. Those two, we've said from the very beginning, is 1. So really, I get 1 plus 2 cosine x sine x, which is what it wanted me to get. Okay? So that's the other one. Okay? Alright, so don't let this freak you out yet. There's more. Let's go to the next page. Okay? And on the next page, you'll see all of the identities. And we've kind of already talked about a few of these. We've talked about how the reciprocal works. And again, we could also say sine is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cotangent. Okay? Tangent is sine over cosine. Cotangent, we just got done saying, is cosine over sine. And then we've got our 3 Pythagorean identities that we just verified on the previous page. We're going to use that to try and solve the rest of this stuff. Now, this one can be kind of difficult because I got to get from here to there. Sometimes it's easier to go backwards from here to there. It's just a matter of how you want to look at it. Okay? So let's write tangent. I've got sine squared theta over cosine squared theta minus, well, sine squared theta. I need a common denominator. My common denominator is going to be cosine squared theta, so I'm going to multiply the top and the bottom by that. Then I can combine my terms here. Sine squared theta minus sine squared theta cosine squared theta all over cosine squared theta. Well, this is a GCF problem on top. I can factor a sine out of both. Sine squared theta times 1 minus cosine squared theta all over cosine squared theta. Why do I want that? Because if I look back to here, is I can minus sine squared to both sides and say cosine squared theta is 1 minus sine squared theta. I can also take this right here and minus cosine to say that sine squared theta is 1 minus cosine squared theta. I can do that with any of these. I can say tangent squared theta is secant squared minus 1. I could say secant squared theta is what we got. I could say 1 equals secant squared theta minus tangent squared theta, and so on. So, why do I want to do this? Because all of this is the same as sine squared theta. Well, now I'm going to rewrite that. Sine squared theta times sine squared theta over cosine squared theta. This right here, sine over cosine, is tangent. So I get tangent squared theta times what's left, sine squared theta. And that's right there. I got what I need. The next one, again, I'm going to start with 1 over cosine squared theta minus, well, this is 1 over cosine squared theta, and then cosine squared theta on top, because that's on top, that would be the reciprocal of the flip. Now, here's the thing, I already have a common denominator, so let's just go 1 minus cosine squared theta over cosine squared theta. I know what some of you want to do, you want to just cancel these out, but let's not do that yet because I've got a common denominator to combine. This right here, we've said over and over again, right there, equals sine squared theta, and then this one becomes pretty easy because sine over cosine is tangent because it's squared. We put that, and I've got what I need here. Okay. Next problem, sine over cosine. Put my thetas in there. Plus cosine over cosine over sine. Put a big fraction by here. Now I don't want to do a common denominator yet, that's for sure. I want to keep it, change it, flip it first. So this is sine theta, keep it, change it, flip it. Cosine theta over sine theta. Plus cosine theta, which is this, times the flip, sine over cosine. And now, because I'm just multiplying, I can extend these lines. And what do I need from there? Well, I don't need anything because look, these cancel, and I get cosine of theta plus sine theta, which is like this if I write it around. You didn't see much of that, did you? I got this fraction because tangent is sine over cosine. I got this fraction because cotangent is cosine over sine. Then I kept it, changed it to times, flipped it to get here. I kept it, changed it to times, flipped it to get here, canceled out common terms. Cosine plus sine is the same as sine plus cosine, which is what is written here. And I got it. Whew. Take a deep breath. That was the hard stuff. This stuff is super easy. Just simplify it, which means cosecant, is 1 over sine. Tangent is sine over cosine. And cross cancel when you can. The sines cancel. I get 1 over cosine, which, by the way, is secant theta. That's the kind of things I want you to do here. Secant, we just said is 1 over cosine, just on this previous problem right here. Cotangent is cosine over sine. So the flip, the reciprocal of tangent, plus it says it right at the top of this page, by the way. The cosines cancel. 1 over sine is cosecant theta. And then for number 9, I'm going to FOIL it out. That becomes, actually, do I even need to do that? No, because look up above. 1 plus cotangent of theta. Look, I have that right here. It's just cosecant squared theta. So let me replace all of this with cosecant squared theta times secant squared minus 1. Okay, if I were to take this and minus 1 to both sides, secant squared minus 1 equals tangent squared. So let me rewrite that as tangent squared theta. Now let me rewrite these as fractions here. So I got 1 over sine squared theta times sine squared theta over cosine squared theta. I can see these cancel. 1 over cosine squared theta. Cosine is secant squared theta. That's it. That's my answer. Okay, again, I'll run through it. This, because of what I have written above, changes to that. This, if I take what I have written above and minus the 1, I get to tangent squared. Tangent sine over cosine. Cosecant's 1 over sine. Cross cancel. 1 over cosine squared is secant squared. Your homework, again, is out of the book. I will copy those pages and put them on Google Classroom for any of those of you who are absent. What we're going to do, actually, for the first night's homework is just... I don't remember. We're doing the evens one day and we're doing the odds the other day. So one day we're going to do 1 through 37 odd. I think that's actually the second day. And then the next day we're going to do 2 through 38 evens. I think that's the homework tonight. Double check Google Classroom. I will write it on there anyway. But I'm pretty sure this is going to be Wednesday's homework. This is going to be Thursday's homework for this week. So have a good day.